Okay, so this example is directly from your problem set. It's going to be number 2. So I'm just going to start off by writing what you were given. And that is an E0 prime of negative 0.52. Okay. Then over on this side, we have 1/2 oxygen and water. Okay. And that's going to be a positive value of 0.82. So the first thing that I'm going to do is identify which side is being reduced and which side is being oxidized. So we learned that the higher E0 prime value is what's going to be reduced. So in this case, I'm going to write GR, which stands for gain electrons reduced. Just to keep that straight in my head. I know that other acronyms exist, such as oil rig, but this is the one that I learned. So then on the other side, I'll write LEO, which is the opposite, and stands for lose electrons. Oxidized. Okay. So next I'm going to introduce oxidation states, and I want to point out that a table on oxidation states used to exist in the older version of your book, but it doesn't exist in the newer version, and we actually didn't know that until recently, so I'm just going to go over that very quickly right now. All you really need to know in this case is that your hydrogens are going to have an oxidation state of +1, and your oxygens will have a state of -2. And this becomes important when you're trying to figure out how many electrons are being transferred. So let's start with the first side of things. I'm just going to write the first one that we see, which is sulfate. So for figuring out the oxidation states, let's start with oxygen. So that's going to be -2 multiplied by 4, and that will be -8. And then you can look here at the overall charge of the molecule to figure out what the oxidation state of sulfur is going to be. So whatever it is going to have to combine with this oxidation state of -8 to ultimately give the molecule an oxidation state of -2, which means that sulfur in this case is going to be +6. So then I'll draw the other half of this. So again, -2 times 3, -6. Hydrogen is +1. And again, looking at the overall charge of the molecule, by default, our sulfur has to be +4. So what's happening here is this is just a way of showing that you're going from a more reduced state to a more oxidized state with the sulfurs, and giving up 2 electrons. So for the other side of things, for the oxygen and water, it's generally good to know that oxygen is a good acceptor, and pretty much in this case we kind of can just flip that arrow, and that's going to help us write our half reaction. So the oxygen is going to be going from a more oxidized state to a more reduced state, because that's what's accepting electrons or gaining them. Incidentally, this ultimately has a charge of 0, as you can see. You can work the math out using the oxidation states and see why that is. And it's the same with water, but we are still transferring 2 electrons. Okay. So that's pretty much the heavy lifting of these types of problems. And it's easy now, now that we've figured out that we're using 2 electrons. So I'm just going to start writing the half reactions, and then we're going to balance them quickly. We identified up here, we have electrons going this way. So we'll start by writing this guy going to sulfate, where it's going to be more oxidized. And then we identified that we're giving up electrons, and that the amount of electrons is 2. So now we can balance it. And in this case, it's pretty easy. So already you can tell that the oxygens aren't balanced. So just add a water. You can pretty much just pull water out of the air whenever you do redox problems. And that makes it pretty easy. After balancing the oxygens, check your hydrogens, because you're probably going to need to balance that, given that you added some to one side with that water molecule. So we have 3 hydrogens on one side and none on the other. So we simply have to add 3 protons to this side, and now it's balanced. And then we will simply do the same thing with our electron acceptor. So we have our oxygen plus 2 electrons, so it's the opposite situation here. And that makes water. So again, we have to balance this. And the only thing that doesn't balance is the hydrogen, so we'll have to add 2 hydrogens to this side. Now it's balanced. So at this point, you're pretty much done. You just have to cancel things out and then rewrite your fully balanced equation, eliminating the things that were canceled out. So I'll show you what cancels. In this case, it's the water, the electrons, and then also you can cancel out those hydrogens and just be left with 1. Kind of reduce that down. So just be sure when you write your answer that you write your final balanced equation, eliminating the things that cancel. And also be sure that you calculate your free energy. So that's just -n, which is your number of electrons. So 2. Faraday constant, which equals, it's like 96.5. And then the change in E0 prime, which is always going to be your E0 prime acceptor minus E0 prime donor. Okay, so just make sure you follow the order of operations, and you should have no trouble. This will eventually come out to be an answer in kilojoules per mole. And then just to figure out how many, or what the energy is per electron, you simply have to divide by the number of electrons. So in this case, 2. And that is it. I hope it helps.